Hi, I'm James Wright. I'm going to give you a little bit of an overview about the kinds of topics that I like to think about and the sort of general questions that I like to ask. And then I'll spend a little bit of time telling you about some of the projects that I have worked on recently and some of the projects that I'm hoping to work on in the near future. And then I'll wrap up by showing you my email address again in case you'd like to get in touch with me. So I'm like everyone else in that all of my research happens at the intersection of various things. So for me, those three things are multi-agent systems, bounded rationality, and machine learning. And so on this slide, I'm just going to tell you a little bit about what I mean by each of those things. So first of all, one of the main things that I think about is multi-agent systems. So I claim that problems are very different when you've got agents involved who all have their own priorities and goals. So I think about this a lot, especially through the lens of game theory. So a lot of my work either operates in game theory itself or operates in something called behavioral game theory, which is more of a bottom-up kind of data-driven version of game theory. So I think about all sorts of things with multiple agents in them. I think about anything that has to do with incentive issues, where you need to make sure that your agents aren't being perversely incentivized to do something you don't want. I think about designing platforms, which again is kind of a different sort of incentive design. And I think about modeling how people are actually going to respond to the incentives that exist. So I distinguish between designing the agents, where I don't get to control the incentives that they're facing, I just need to do a good job of optimizing against them. I contrast that with platform design, where instead I don't get to design the agents themselves. Instead, I have to design the platform that the agents are going to interact on. And so I want to make sure that the agents who are interacting on that platform are incentivized to behave in some desirable way. The second big theme in my research is bounded rationality. And again, I think about that both in terms of people and in terms of computation. So again, I distinguish between two different flavors of bounded rationality research. The first is descriptive. So game theory assumes that everybody is perfectly rational, but of course we know that's not true. And so the descriptive version of bounded rationality says, since people are not actually perfectly rational, it turns out that the predictions of game theory about how they're going to behave often aren't accurate. And so instead we can think about something called behavioral game theory, where we try to treat this as a prediction problem, where we try to figure out a good model of how people actually behave in these situations, rather than starting from the assumption that they're rational and deriving how they must therefore behave. The other direction that you can go when you're thinking about bounded rationality is normative. You can think about the question of how should an agent behave when they're boundedly rational. And this is a very thorny question, right? Because it basically says, suppose I'm not allowed to optimize. I've got some preferences, but I can't perfectly optimize them because it's too hard. What should I do instead? What is a desirable criterion for me to shoot for? And there's different answers to this question. There's all kinds of different approaches you can take, including things like regret, but also including things like approximation, satisficing, that sort of thing. And the third is machine learning understood very broadly. So I typically think about machine learning either for reasons that are inspired by one of these other themes, or because I can apply it to one of these other themes, or because one of these other things can be applied to it. So machine learning is the least likely to be a standalone theme in my research. It's more likely to come in combination with one of these other things. So some of the things I've used machine learning to think about are, again, these predictive models. You can treat it as a modeling question where you think about cognitive modeling, but you can also treat it like a machine learning problem, right? If I put some situation in front of people and I want to ask how they're going to act, then really that's an input and a response. That's a feature and a target. And so you can treat that as a regular supervised learning problem. Some of the other issues that come up with machine learning are things that have to do with how people respond to machine learning. And so some of my students have done some work on algorithmic fairness. And the angle that we take is that this is a system with multiple agents. People's interests may conflict. And so we take a descriptive approach where we say, well, what do people actually perceive as fair? And I'll talk about that a little bit more on the next slide, I guess. Finally, one of the things that I've been recently getting into more is regret-based algorithms. So of course, that's big business here at U of A, and I'm excited to be part of it in my own small way. And so again, regret-based algorithms are very appealing because they have this bounded rationality character. It's typically, when we think about regret, it's because it's intractable for us to directly optimize. And so we optimize this easier benchmark. And that turns out, as we know, to be quite powerful in some applications. Okay, so this slide is daunting to look at. It's just a laundry list of various projects that I have on the go at the moment. Okay, and this is mostly intended to give you a flavor for the way in which I tend to work in these areas. So the first bullet is descriptive algorithmic process fairness. So that's a mouthful, but that's basically just asking what influenced people's perception of fairness in the context of algorithmic decision making. So this is the fairness in machine learning project that I was talking about earlier. One of the things that I also think about with regret minimization algorithms is how they relate to some concepts in game theory. So of course, regret minimization isn't inherently multi-agent, but you can use it in multi-agent settings. And it turns out that when you do this, the exact versions of regret benchmarks that you use influence the kind of equilibrium that your agents will wind up in. So it's well known that people, or agents really, who all use who all minimize their long-term external regret, it's well known that they'll wind up in something called a coarse correlated equilibrium, which is a much weaker version of equilibrium than the typical game theoretic notion of Nash equilibrium. But it turns out that when you're in a sequential setting, where people make multiple decisions as part of the same game, so this is something like poker or tic-tac-toe or anything like that, in those situations, if you are doing, there's multiple different kinds of regret that you can be targeting, and there's multiple different ways that you can make the regret minimization problem tractable. And depending on which flavor of regret minimization you choose, you're going to wind up in different refinements of this coarse correlated equilibrium, different subsets of it. And so I have some work that studies what those relationships are. And I also, looking forward, would like to think about what the implications of that are for applying these algorithms in situations where they're happening in real time. Okay, so a lot of the time, regret-based algorithms are used basically to find an equilibrium. So some of the most successful applications of regret minimization have included situations where you play the agent against itself, you do a bunch of self-play. Regret minimization is what we do during the self-play. And at the end, you've got a trained agent that is playing something close to an equilibrium. And that turns out to be a good thing to do in a zero-sum game. But I'm interested in what would happen in the situations where you're not in a zero-sum game, and so equilibrium is not necessarily the right thing to do. How would these regret-based algorithms interact in those situations? Okay, another project that I have on the go is called behavioral econometrics. So econometrics is the process of figuring out something about people's values or something about people's preferences just by looking at their actions. So it's kind of like inverse reinforcement learning. Typically, econometrics assumes, again, that people are perfectly responding to their incentives. Behavioral econometrics says, but they probably aren't. And so can we still make some estimate of their values, even if we assume that people are imperfect in this boundedly rational way? Okay, I'm not going to go through literally all of these, but I'll touch on 3 more. Okay, so first of all, I'll just touch on alternatives to utility theory for boundedly rational sequential decision making, which again, it's a mouthful. There is a very strong argument that rationality really kind of, in some sense, means maximizing the expected value of some scalar quantity called utility. So this is related to the reward hypothesis from reinforcement learning, but it's not exactly the same thing. However, the argument makes certain claims about what it means to be rational. So you start from a bunch of axioms about how rational agents must behave, and then you go from there. But if you have different axioms, then you wind up with different notions of what the agent should be targeting. And if you start with stronger axioms, then you can narrow down what kinds of quantity people should be maximizing. So with a utility theory, the number of admissible or permissible utility functions that you can optimize is nearly unlimited. But with additional axioms, you can put further restrictions on those utility functions to sort of make them more rational, but to better identify what people should do. And so I'm interested in alternatives of that kind, where I'm either strengthening utility theory or starting from entirely different axioms, with an eye towards something tractable, right? With an eye towards something that a boundedly rational agent could actually possibly compute. Okay, another project that I have on the go is studying fake news, basically. So it's saying we're going to look at the disinformation problem, and we're going to look at it through the lens of an economic body of work called principal agent problems. Okay, so the idea here is we want the platform to do something, but the platform's interests are not the same things, are not identical to our interests. Our interest is society. Okay, so society is harmed if certain kinds of disinformation are out there. They can prompt certain criminal behavior, say. But because of externalities, the platform won't directly bear the cost of those consequences. Instead, the platform only cares about the consequences that it does bear, which tend to be things like increased engagement and so on. And so this is not the only principal agent problem that we've ever encountered in regulation. And so what we're doing here is we're looking at regulating social media platforms, basically, through this lens, through the lens of how can I regulate an agency where I can't quite tell how much effort they're making. Okay, so what makes platforms, or social media platforms especially, special, one of the things that makes them special, is that we can't tell how hard they're working to detect harmful content, right? If they're using some kind of machine learning algorithm that's similar to spam detection, there's no way for me to directly inspect whether they're trying to do a good job or not. And so this is a very similar flavor to what's called partial monitoring in principal agent problems, where you can't monitor the agent's effort level. And so again, we're applying models from the economic world to the algorithmic world and trying to make progress in that way. Okay, the final project that I'll briefly highlight, because it might be sticking out like a bit of a sore thumb, is I'm also very interested in a certain kind of robust machine learning in what I call opaque domains. So opaque domains are domains where you don't really know what makes things similar. So what do I mean by that? So if you've got a couple of images, I can usually tell if they're pretty different, even if I don't exactly know what's in them. Pixels are a pretty natural representation. They already have lots of spatial relationships embedded within them that turn out to be important for vision. And so I have some hope of telling whether these things are similar or not. There's other domains, such as behavioral game theory, where I actually don't even know exactly what the features are of games that people are keying off of. So games are these kind of funny things where you can, normal form games, especially these simultaneous move games like rock, paper, scissors. They're these funny sorts of things where I can represent them as a matrix of numbers, but there's the spatial relationships don't really matter. These things are permutation invariant in the sense that if I permute the rows and columns of my matrix, it's basically the same matrix. Right? It's up to permutations, basically the same thing. And furthermore, I can't really tell if two games are similar or not in terms of how people will respond to them without some kind of underlying model. Right? So it may be that the payoffs might be very, very different, but the games themselves might be strategically equivalent. So in these domains, we want to be able to not accidentally overweight certain games that are all kind of the same. So this is the motivation for my interest in this area. And we've got some pretty interesting results. Okay, so just briefly in the next couple of minutes, I'll just spin through some other prospective projects that I'd be interested in working on. And this is not an exhaustive list. So one of the things I should emphasize is that in my group, typically what happens is students show up, I take them on or not. When I take them on, it's not always with some particular project in mind. And in particular, I don't have a list of projects that I'm waiting to match up a student with. What I'm interested in is I'm finding students whose interests are compatible with mine, who have some interesting ideas about what they'd like to work on. Okay, so it's this collaborative process of figuring out what the project should be. However, having said that, here are some things that are kind of on my to-do list or sort of my nice-to-haves list. Okay, so one of the projects that's related to the equilibrium project I described, I'm very interested in the limits of self-play. Right? And this is very related to the equilibrium in which agents will wind up. So training agents with self-play in a zero-sum domain is basically just going to work. Right? There's technical problems, but mathematically this is just a sensible thing to do, and in some sense it's the most sensible thing you can do. But when you're in a situation that isn't zero-sum, things get a lot more complicated. And so I'm interested in what are the situations that are kind of like zero-sum games, and that self-play gives us something that we might hope to deploy outside of the training regime. I'm very interested in predicting sequential play by humans. Okay, so I'm very interested in behavioral game theory models for sequential play. Most of the behavioral game theory models I've worked on so far have really been about instantaneous decisions. They've been about simultaneous games where people kind of make one choice and then they stop. Turns out that's pretty rich even by itself. But of course, you get a whole new world of things to think about when you're thinking about sequential play. And so I have some ideas there that I'd like to explore. I have some existing machine learning models of human behavior. They work really well. I don't know why. It's kind of the standard question with neural networks. But I'd actually really like to inspect what they're doing. I'd like to get some notion of what they're doing and what the features are that they're keying off of, mostly just for understanding. So I think that one of the things that I think is underexplored with machine learning is using trained machine learning models as an instrument. Okay, so I train something that does a really good job of prediction, and then I try and figure out why. I think that's hard, but I think it can be quite valuable. I think it can produce real insight. I've put alternatives to utility theory for boundedly rational sequential decision making on this slide, just like I did on the last slide. This is a project that I think could admit of multiple directions. Okay, and then just kind of as a list of other possibilities, traffic modeling is always an option for multi-agent systems. I worked on it years and years ago, but I would be interested in coming back to it. You can ask questions about how topics should be selected in election coverage. So this would be more of a theoretical exercise where we're thinking about what kinds of information make sense for good aggregations of information in an election. Behavioral finance, of course, is a perennial favorite for behavioral game theory. I've done some work on peer grading platforms, and so if people are very interested in that, that's always a possible direction. And finally, what I called platform design is more standardly called mechanism design. And so I'm interested in all kinds of questions around mechanism design. And that can be either through the lens of behavioral game theory or through the lens of regular game theory. Okay, so that's pretty much what I wanted to tell you. I'm looking for a couple of students, one or two this term, or this year rather. I'm looking to recruit a couple of students to work on projects like this, not necessarily exactly like this, but somewhere at the intersection of multi-agent systems, bounded rationality, and machine learning. So if any of this sounds interesting to you, please do get in touch. You can email me at my email address here. It's just my name with a dot in it. And another direction that you can do if you're sort of interested, but maybe not sure it's right for you, is to attend my reading group. So I have a weekly reading group where members of my group, we all read a paper together, and then somebody presents it. We do this every Monday. And it's a great way to get a handle on how my group interacts, the kinds of questions that we're interested in, the kinds of things that we like to talk about when we read a paper, and really just what everybody's working on. Most of the time what we do is the students select papers based on their own interests, and so you can kind of get by osmosis just what sorts of things tend to tickle our interest. So thanks for listening, and I believe I'll be around for questions as well.